Okay, you guys, we are going to look at section 2.3, which is the modern view of atomic structure. So at this point, you've watched some videos and you've learned kind of how did we come up with the current structure that we have. Remember that atoms are smaller than we can see with the human eye. We don't really have any technology to see inside of an atom. So everything that we know about atoms has come from those experiments, the gold foil, the cathode ray tube, Millikan's oil drop experiment. That's the information that we have, okay? So our modern view of the atomic structure is basically that we have this really dense nucleus in the center. And when we say dense, what I mean is that it has most of the mass in the atom. And then outside of this, we've got this empty space. This is called the electron cloud. It's not a completely defined space. And within the electron cloud, we've got electrons. Remember, are negatively charged, really, really small throughout there. So we can see that most of the space in an atom in this electron cloud is empty, and then it's filled by just a few of those small electrons. Okay, so these subatomic particles, sub meaning inside the atom, we have protons and electrons are the only particles that have a charge. So protons, we can see down in this table, have a charge of +1, and electrons have a charge of -1. And neutrons are neutral, meaning they have no charge. So if we're going to write these kind of shorthand, proton is a lowercase p with a plus, neutron is a lowercase n with a 0 or a naught, showing no charge. And then electron is a lowercase e with a little negative. Another thing we know about these subatomic particles is that protons and neutrons have essentially the same mass. So we're going to measure mass in AMU, which is atomic mass units. The reason that we do that is that the mass in grams or in kilograms is a really, really, really small number, like 10 to the -14th, I believe. So instead of doing that, we have given it this value of kind of 1 if we're looking out to kind of 2 or 3 sig figs. And so the mass of a proton and neutron are essentially 1. And the mass of an electron is 5.48 times 10 to the -4th. So that would be this number here with 3 zeros. So if we were to add this to this value with the correct number of significant figures, it doesn't actually change the number at all, which is why we don't include electrons in our calculation of mass. Okay, so there are a couple of different ways that we can kind of represent elements. So for elements, we're going to use the symbol. It's either 1 or 2 letters. We've looked at these already. This one here would be carbon. If there are 2 letters like N and A, the first one is always capitalized. The second one is always lowercase. Now we can use something called symbolic notation, and it gives us a ton of information about an element, just kind of a small symbol. And so the first part of it is that the symbol of the element is there. Then we're going to add in the atomic number, and the atomic number is on the periodic table. Remember, it's in order by atomic number. And the cool thing about the atomic number is it tells us how many protons and how many electrons there are in a neutral atom. So if I'm looking at atomic number 6 of carbon, I have 6 protons and 6 electrons, okay? All atoms of the same element have the same number of protons. The third piece of information that the symbol can give us is the mass number. The mass number is going to be a whole number, so there's never any decimals, and it's the number of protons plus the number of neutrons. And remember, we don't include electrons because they're so small, they don't actually change the mass at all. So in this one, we can see that since there's 6 protons, which we found with the atomic number, and our mass number is 12, there must be 6 neutrons. So I can use this symbol here to help me figure out a bunch about my atom. It's actually set up really nicely that I can do 12 minus 6, and that tells me how many protons that I have. Or sorry, not protons, neutrons that I have, okay? So we're going to use this to do some calculations, but one thing we need to know is that there are different types of the same element. So isotopes, it's the same element, but it has different masses. Now, remember, the protons come from the atomic number. The electrons have nothing to do with the mass. So when you have an isotope, it's the neutrons that are changing. So the neutrons don't change the charge at all. It's going to remain neutral, but we can add or take away neutrons. So if we look at carbon, carbon has 4 common isotopes, or 4 isotopes. They all have 6 protons because they're atomic number 6. They all have 6 electrons because we need to cancel out the positive and the minus. The neutrons is what changes. So this one here is carbon 11. We can also write it like this. If there's 6 protons, but the mass is 11, we would take 11 minus 6. That gives us our 5 neutrons. Okay, here we have carbon 12. Okay, our 6, 12 minus 6 gives us our 6 neutrons, and we can keep going. One of the isotopes is usually more abundant, or there's a higher percentage found than the other one. So in nature, almost 99% of carbon is carbon 12. So we're going to do some practice with calculating protons, neutrons, and electrons. So you're going to need your periodic table. If you have not gotten it out already, go ahead and do that. So we're looking at copper 63. So copper 63 has a mass of 63. And when I look up copper, copper's atomic number is 29. So again, this notation here is going to give me a lot of information. So we're atomic number 29. And remember, atomic number is the same as the protons and the electrons. So if I have 29 as my atomic number, I have 29 protons and 29 electrons, okay? Then I need to calculate my neutrons. So remember, if I've got my isotope notation here, I'm just subtracting 63 minus 29, and I end up with 34 neutrons when my mass is 63. And remember, the mass can change in an isotope. So right below it, I see copper 65. So I'm thinking to myself, okay, copper 65, my mass is now 65, but it's still copper. So it's still atomic number 29, still 29 protons, still 29 electrons, but now I have 2 more neutrons. So my mass has gone up by 2. So now I have 36, okay? So go ahead, you guys, and pause the video for a moment and fill this chart in. Okay, so hopefully you paused the video and finished filling out your chart. That the mass number is a whole number, but when you look at the periodic table, so you guys, we noticed there is an average atomic mass. So the average atomic mass has to do with all of those isotopes being averaged together. And what we use is a spectrometer in order to do this. So the spectrometer gives us kind of a breakdown of the different masses of the things in there. So in this one, we're looking at chlorine. And so we can find out how many different isotopes of chlorine there are. So we end up with something like this. This is our mass spectroscopy graph. And the mass spectroscopy graph, gives us the information of the relative abundance, so kind of how many are this form, and then also a mass to charge ratio, which basically tells us the mass number. So we can see that there's 1, 2, 3, 4, 5 different types of zirconium. So zirconium has 5 different isotopes, and remember, this is different number of neutrons. Okay, each of these have a different mass, so 90, 91, 92, 94, and 96. Okay, the graph can also tell us that zirconium with a mass of 90 AMU is the most abundant. So it's like maybe 52% zirconium 90, all the way down to zirconium 96 is down here at like maybe 2%. Okay. And then the average mass will be closer to 90 than 96. So since more of the zirconium is zirconium 90, the mass is going to be closer to that. So if I look at my periodic table, zirconium is number 40. The average mass is 91.22 AMU. So we see that it is closer to that value than to the 96 because there's hardly any of that 96. So I want you to take a second and analyze this graph here. So we don't necessarily know which element it is. There's not a title up here. So we can find that out though by analyzing the graph. So take a second and try and answer those 4 questions. Okay, so hopefully you took a second to look at that. So it has 5 isotopes because I've got 5 lines. The most abundant or the tallest is this 74. The average atomic mass. So looking at kind of the most abundant, I know that it's not going to be out this way. So it's going to be somewhere in here. And since these 2 are my most abundant lines, it's probably going to be somewhere in between 72 and 74. So I put about 73. So when I look at my periodic table, I see that germanium has a mass of 72.59, and then arsenic is 74.922. So that would be above 74, and so I know that it can't be arsenic. So the next best option would be germanium. So I can look at my mass spectroscopy and I can kind of guess what my average atomic mass is going to be near, but we can actually calculate it as well. So average atomic mass is a weighted average. It's an average like we do our test scores. So where the test is worth 80% and our assignments are only worth 20%. So some of the masses have more pull. And so this average atomic mass is calculated by looking at the weights that we just saw in the spectroscopy, and then also their relative abundance. So this is our kind of calculation here. We're going to take the sum, and for sum, we're going to add the mass contributions for each isotope. So to find the mass contribution, that is this right here. We're going to take the atomic mass times the percent abundance. And remember, when you multiply by a percentage, you need to move the decimal back too. So let's try one of these. So naturally occurring chlorine has 2 isotopes. We want to calculate the average atomic weight of the chlorine. So first we're going to find the mass contribution for each isotope. Sometimes we're given it in a form like this where it's just, we would use 35 of the chlorine. Sometimes it's given with us a little bit more detail. So if we're given that detail, that's what we want to use. So our mass contribution is going to be, I'm going to say MC. The mass contribution, remember, is the mass times the percentage. So for chlorine 35, my mass is 34.969. And then I'm going to multiply it by the percentage. So remember, you need to move your decimal back 2 when you are multiplying by a percentage. So 0.7578. So 34.969 times 0.7578 gives me a value of 26.4, and I'm going to keep all the decimals because I'm not ready to round yet. So that's my mass contribution of chlorine 35, but it's not 100% chlorine 35. So I need to add in my contribution from chlorine 37. So I'm going to take 36.966. Again, when I multiply by a percentage, I need to divide by 100, so 0.2422. So 36.966 times 0.2422. Now I'm multiplying by a smaller percentage, so I'm going to assume that my contribution will be less, which is what I see here. So it's just like, it's important to do your formative assignments, but they're going to contribute less to your grade than your summative. So to find the total average mass, I'm going to add those 2 together. And again, I'm kind of keeping all my decimals while I'm adding. And then I was given percentages in 4 sig figs. So I'm going to do my answer to 4 sig figs. So, okay, so when I do it to 4 sig figs, it is 35.45 AMU. And when I check the periodic table, chlorine does in fact have an average atomic mass of 35.45. Notice also that my mass is much closer to my 35 than my 37 because it has a higher mass contribution. Okay, you guys, there's one more example in here, so I want you guys to try it. And in this one, I don't tell you what element it is. So after you have found the average atomic mass, go ahead and look at your periodic table and try and identify the element. Okay, so go ahead and check your answer. Make sure, again, when you're multiplying by the percentage that you're moving your decimal back twice. So with our 6.015 mass, we need to add a 0 in there. So we should have gotten 6.94 AMUs, which is lithium.